to survive. How this, the effect of heat on the growth of the tree is more apparent in this diagram, where on the shadow side of the trunk, so to speak, then the annual rings tend to be close together, the sap waves are finer, the movement of sap up and down the tree on that side faster, whereas on the other side of the tree, which is exposed to sunlight, then the annual rings become wider, the material between them pithier, and the movement of sap slower, and under normal conditions a lot more branches would grow out from that side, making the timber virtually useless because there would be too many knots in it. And when sap moves up and down the trees, in a healthy tree, and a shade-demanding tree in this instance, in this proper environment, then there are virtually no branches which are produced on the trunk. The trunk is virtually cylindrical, and because there are no branches, there are no impediment to the movement of sap going up the tree. So it can rise to the top of the tree, which could be 150 or 200 feet high. And the sap waves are very small, the sap ducts are very small. And now, how does the sap get up there? Because, of course, under normal suction, you can't raise water up more than about 9.8 meters by suction. And osmosis won't take you that much further either. So how does the sap actually get up there? Now, according to Viktor Schauberger, as the day warms up, or as the climate warms up, the season warms up, there's a general rise in temperature, and all the carbonic acid which is in the sap, which is in the water, gradually warms, and a certain portion of it then turns into carbon dioxide, which is a gas. And these bubbles of gas then fill and block off the sap ducts, and like corks they rise and they push the sap and the water ahead of them right to the top of the tree. And at night, when it cools slightly, they fall down, and then they draw in all the sugars and starches and the nutrients and the gases which have been formed during photosynthesis during the day. So that's what happens when you have a naturally grown tree with very tightly spaced annual rings. When it is a plantation tree, then the rings are wider apart, there are more branches, but also the sap ducts are commensurately wider apart, but the bubbles of carbon dioxide are not sufficiently, they don't expand to fill these ducts in the same way as they expand to fill these ones. And so the sap is not lifted, the nutrients are not lifted as high as they would be in a healthy tree, and therefore they deposited at the base, which is why these trees then are more cone-shaped at the bottom. Instead of being straight, then they have this shape, which of course everybody thinks is ideal for a Christmas tree, very picturesque, but actually a Christmas tree like that is a very unhealthy tree. Trees have a function. Not only do they give us oxygen, but they also have a symbiotic interaction with trees, in that they provide for us the color we need most for rest and peace of mind, which is the color green, because trees absorb light by and large in the ultraviolet violet part of the spectrum, and the infrared and the red part of the spectrum, but they do not absorb light in the green part of the spectrum, so that is what is not absorbed is reflected. We, on the other hand, are not very sensitive to ultraviolet or infrared, but we are very sensitive to green. And green is the color that the trees give us, and if there's a lack of greenery, then I think it has quite an effect on the psychology of the people who are living in such an environment. In many modern cities there are very few trees, and I think this must lead to an increased violence, a fundamental rising of the disturbances in the nervous system, and also of course then there's a lack of oxygen, which produces anoxia and various other things. Trees can also be likened in Viktor Schauberger's to biomagnets rather than magnets. A magnet we usually view as being a bar magnet, which has a north pole and a south pole, and the magnetic lines of force go from the south to the north, and they spread out across the middle. And that is generally what our view of a magnet is. However, a tree has a completely different form of being a magnet. This is one which is based on a hyperbolic cone. Again, this is actually a bit cone-shaped in form, but if you can see the way the forces arise inside this tree, that there is, this is an experiment I carried out, so I measured exactly where all these filings are moving to, and out of the top they flow, out of the top they flow in towards the sides, and they flow in from the bottom. So in a sense you can get a picture of what this form, the hyperbolic cone, is again to do with non-Euclidean geometry, which is the geometry of nature. And so you can see that a cone taken in this shape seems to already give the pattern for the growth of the tree, because all the way all the filings on this are disposed gives a very tree-like form. If we come back to if we were to view these as the annual rings on a tree, water, as I think I mentioned when we were talking more about water, has a dielectric value. It is a very high dielectric value, which means it's able to resist the transfer of charges from one side to the other of it. If in the tree we have the green part is water, which eventually then becomes the annual ring, then on each side we have positive and negative charges. As the surface area of the outside blue cylinder is larger than that of the inside red one, then the density of charge, the intensity of the charge on the inside one is greater than it is on the outside one. And as a tree is made up of a series of concentric rings, then the charge from the outside increases as we move towards the inside. But under certain conditions, the energy of the tree can be severely disturbed because of the distance and the spacing between it. Now, when we're looking at the terms of separated charges of positive and negative, the closer the charges are together, the greater the potential. In that sense, the greater the life force. The further the charges are separated apart, the lower it is. Now, here we have a 33-year-old tree, a section through the trunk, and you can see straight off that this was a plantation tree because the annual rings in the middle are very widely spaced apart. That means that when the tree was a young, struggling little tree, a sapling, it was exposed to far too much sunlight. And so its girth widened at the base, and gradually, as its neighboring trees grew up, then it became more and more protected from the sun, and the annual rings got closer and closer together. At 26 years old, someone came and cut down all the trees around the outside of it, and at once all the annual rings then expanded. Now, the time that this tree was actually healthy was in this part of its life, whereas here it was unhealthy, and in the center it was unhealthy. And in terms of the life force, the potential, so to speak, between here and there, the life force would have been much less because the charges of positive and negative were separated by much greater distances. Here they would have been very close together, and so the two charges would have been closer together and the potential much greater. And so this graph at the bottom here, the blue one, shows you really what the potential levels are, their nominal values, as you move from the outside to the inside. So from here to here there's virtually nothing. Suddenly they peak because they get very close together, it falls off, and then from there to there's nothing again. On the other hand, the actual generation of a charge from the outside to the inside does increase constantly. It's difficult I have to differentiate between potential and charge. Potential is the life force. It's a different energy from the electrical charge, which can be measured from the outside towards the inside. Walter Schauberger made some probes, and he probed one probe very deeply into the center of the tree and the other one on the outside, and in that way he was able to make light bulbs light up. I'm not sure whether I haven't mentioned that already, but